In this video, I hope to go through the test hypothesis topic with you. I want to review it quickly, and then I want to go and take a look at a couple of examples. We're going to work just with a single population mean here. And so our test hypothesis that I've talked about before, I mentioned that there are 4 steps that you need to be very familiar with. The first one, which is always your responsibility, is to formulate or identify the test that you want to conduct. And the test that we've talked about is comprised of 2 different hypotheses. There's a null and there's an alternative hypothesis. And it's your job to specify exactly what it is we want to test. The null hypothesis is the one that we typically list first, but it's not the one we typically think of. It's the alternative that we think of. There's a story. Somebody wants to learn about a population mean. They want to test to determine if the mean da 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 exceeds 400. And so we would write an alternative there of mu greater than 400. The da 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 is just a story that they're telling us. It varies quite a bit from one problem to the next. In another problem, it may have something to do with the population proportion. And one of the things we're going to see is a whole bunch of different applications of this test hypothesis topic this semester. In fact, in the next slide, I'll show you all the different applications that I'm going to show you that I'm going to work with you on. The main thing, though, is if you see it, if you see all those applications as being the same thing, it's the same process repeated over and over and over again. The sooner you learn the process, the easier the applications later will be. And so that's what we're talking about here. You formulate the test. You got to specify the null and the alternative. That alternative hypothesis is actually used in the software program that you're using to generate a printout. And on that printout should be a test statistic. And so this one comes first. A lot of times folks look at the printout. I'll show you in the next, or in the first example. I'll show you the printout and I get a question, why do I need to do this? It's sitting there on the printout. I'll talk about that. So the test statistic will be found on that printout, and then we have to evaluate that test statistic. We have to take a look at that test statistic and try to determine what it's trying to tell us. The theory, the thought process here is, if the null hypothesis is true, we know what to expect. Our understanding of sampling distributions. And you probably looked at it closer in your first statistics class than I looked at it with you this semester. But our understanding of sampling distributions helps us to understand what should happen if we were to take a sample. When the null is true, we will end up getting a distribution that we know about, like a z distribution or a t distribution. And later on this semester, we would learn about f distributions and chi-square distribution that goes all over the place. But once I understand what to expect, I have a pretty good understanding of when I'm not seeing that. If I know what should happen, then I can identify when it's not happening. And here's how it works. If the null is true, this is what should happen with the test statistic. Well, what happens if that's not what you see? Well, the conclusion we reach is if we get a test statistic that is unexpected, we're going to reject the null hypothesis. And there's a couple different ways of doing that. The evaluation of the test statistic, you probably learned initially when you first did this stuff, you probably learned something called a rejection region approach. And that's where you went to the distribution, again, t or z is probably what you use, but you went to that distribution and you tried to figure out now what's expected, and more importantly for the rejection region, what's unexpected. If we're doing this test, what shouldn't we see? And that's what the rejection region told us. And so it usually specified values in the tail or maybe both tails of the distribution. It said, yeah, you shouldn't be here. If the null is true, you shouldn't be out here. And if we saw a test statistic that was out there, we'd be like, we don't believe the null. That's the rejection region approach. And it's a fine approach. It requires the use of tables. And so I'd have to introduce the t and the z, which you probably have some familiarity with. But later on, I'd have to introduce you to some new distributions. Probably what you've never seen before, the chi-square, the f distribution are the two that come to mind that we use this semester. So all that's a possibility, and it works fine. It works great. A lot of people love rejection regions. Or we can use something called the p-value approach. And I've talked to you about the p-value approach before, but the p-value approach in a nutshell says rather than taking a look at what's expected or what's unexpected, let's take a look at the probability surrounding the test statistic. For instance, if the null hypothesis is true, I should see one of those typical test statistics that I expect. If the null hypothesis isn't true, or if the test statistic's way out there and further away than where I expect in that unexpected region of the rejection region, then the probabilities attached to it are going to be pretty small. And so the p-value tells us the probability of seeing something further out there than what we observe. So the smaller the p-value is, the less likely we believe the null hypothesis. So small p-values indicate reject H0. In fact, you might remember me telling you when p is low, the easy way to remember it is reject the hoe. It's kind of funny, it sounds weird, but it really does stick, and it's easy to remember. When p is low, reject the null hypothesis. And so we're going to take the test statistic, which is found on that printout, and the p-value, which is also found on that printout, and we're going to make our conclusion. And so that's where you tell me what you're going to do. Are you going to reject the null hypothesis, or are you going to fail to reject? And then there's some words, and we'll take a look at the wording a little bit more later with some examples. And so those are the 4 steps you got to get comfortable with. Every test that we see, every application of a test, a hypothesis that we run into, is going to have those same 4 steps. Test, test statistic, rejection, not rejection reason, excuse me, test statistic, p-value, that's a smarter, more efficient way of doing it, conclusion. Test statistic, p-value, conclusion. The sooner you become really, really good at that, the easier this class becomes. The sooner you get really, really good at interpreting confidence intervals, I should say, the easier this class becomes. Because these applications that you see here, we're going to see confidence intervals and test the hypothesis in each of them. Everywhere you look, there's going to be a confidence interval or a test, and sometimes both. When you do 3 or more means, 3 or more proportions, we begin with a test the hypothesis, then we do some confidence intervals. Same thing here. Confidence intervals, test the hypothesis. Test the hypothesis, confidence intervals. We see them everywhere. So you got to get good at them. Now, for the purpose of this video, I want to concentrate here. Let's start you off with just a population mean. We're reading a story, and it's going to have something to do with a population mean, and we want to do a test. Now, you can see that over here, we have a large sample that would utilize the z-distribution if we were into such things. There is a small sample that will use the t-distribution. If we were working with rejection regions, we would have to get into the nitty-gritty of it. We're not. We're p-value people. And so we're going to let that distribution part of the problem, we'll let the computer do that. It's really good at stuff like that. Let's let the computer do the math, do the formulas, do the distributions. Let's you and I worry about the bigger picture stuff. Now, what does this mean when we have large in sample? Is it going to affect us at all? Yeah, it will. We'll talk about some assumptions. The small sample test is going to require an additional assumption that the large sample test doesn't. You may remember something called the central limit theorem. It's something you looked at in your Stat 1 class. It said, you know what, when you have large samples, you don't have to worry about the shape of the population. When you have small samples, you do. And so it shows up as an extra assumption. Everything else is pretty much the same. So let's take a look. I got 2 examples for you. I have a large sample test and a small sample test. Now, when we say large and small, how do you know? This particular problem sampled 36 funeral homes. We're trying to work with the average full service funeral fee. And in 2009, this problem tells me it was $6,500. We sample 36 funeral homes, and what we want to do here is conduct a test to determine if the average in the current year exceeds what it was in 2009 and exceeds that $6,500. But how do I determine if this 36 is a large or a small sample? Well, it depends on the criteria you're using. Here's where I want you to be very careful. Large sample depends upon what it is you're doing. Here we're working with the population mean. A lot of you guys remember it's a very easy sample size criteria if n is greater than or equal to 30. Some of you in a prior class may have used 25. Depends where you took your Stat 1. That's fine. Typically, most folks use 30, but some people use 25. Either way, this is greater than or equal to 30. It's a large sample. Here's where I want to caution you, however. That's typically the first sample size criteria you run into. It's not the only one. If this problem was working with a proportion of some sort, 30 has nothing to do with whether the sample size is large or small. We'll cross that bridge when we get to it. If you were doing a regression problem, 30 has nothing to do with whether the sample size is large or small. Completely different sample sizes, or say it this way, completely different sample size criteria based upon what you're hoping to accomplish. And so before you answer the question, is this a large or small sample, ask yourself the question, which criteria am I using? This is a problem that deals with means. 30 or more is our sample size. This is a large sample problem. All right, so it says to conduct a test to determine whether the average fee exceeds the average collected in 2009, $6,500. Mu greater than 6,500. That's the formulate part. That's the identify the null and the alternative. And what I just found there, what we're trying to show is the alternative hypothesis. Now, the next part of the slide that you see, I wanted to try to space it out pretty well. You see the printout, and you see right here that the null and the alternative are listed. And sometimes I'll get students that say, why do I need this? Why do I need to come up with the null and the alternative? It's sitting right there on the printout. Well, it's sitting right there on the printout because I went into the software and I said, let's go to the menu that works with a single population mean. Let's test. I had to actually enter the number 6,500, and I had to push a button in the software that I use that said greater than. I said, let's do a greater than test to compare mu to $6,500. Now, you may be looking at it saying, wait a second, that doesn't say 6,500, it says 6.5. Yeah, it does. The data for this problem was in thousands of dollars. And so if a funeral home reported their full service funeral fee in 2000 or in the current year, that's the data that was reported in the current year, if they reported it to be $5,200, it showed up as 5.2. If it was $9,700, it showed up in the data set as 9.7. And so you need to adapt your printout, what you ask for, based on how the data was collected. So I put that data into the software. Because it was in thousands of dollars, I had to take my 6,500 value that I was interested in and convert it to thousands of dollars as well. Hopefully that makes sense. This came first. The alternative hypothesis is what I used to generate this printout up here. Okay, sure, this shows up on the printout, but it shows up only because I had already identified it. So that's always on you. You're going to have to come up with the null and the alternative for me. And then you can see from this printout, you can find a test statistic, you can find a p-value. And depending on the software, the labeling, sometimes they're in columns, sometimes they're in rows. It depends what you're using. But that's always going to show up on the printout. Now later on in the semester, we're going to see some p-values. The p-values that you get on the printout aren't always the ones you want. Sometimes the test you're conducting, sometimes the software you're using, it doesn't allow you to pick the direction of the test. Sometimes some of the software programs only give you not equal to tests, and so there's some conversion that needs to take place. You have to be able to take a look at p-values and make sure you're using the right one. When you're doing a greater than test and you want a greater than test, you just take the p-value right off the printout. And that's how it works most of the time. But now you have to can make a conclusion. Is P low? 0.06 sure seems low. Seems low until you consider the alpha that you're testing at. And just keep in mind, alpha is related to the reliability level or confidence level. If you're 95% confident, alpha is 0.05. That's what we're working with here. If instead I wanted to be 90% confident, then I would use an alpha. What's the opposite of 90%? 10%, 0.10. And so when I have that little expression or make that little expression, when P is low, reject the null, how I determine whether P is low or not is by comparing it to the alpha. In this case, P is not low, P is high. P is bigger than the alpha. When P is low, reject. When P is high, I would love to have something that rhymed with high, but I haven't come up with anything that works yet. When P is high, fail to reject the null hypothesis. I got nothing better than that. Fail to reject the null hypothesis. And so what you'll see me write here is at alpha equal 0.05, we fail to reject. Now, what are the words? What's that mean? Well, there's only two hypotheses. You have a null and an alternative. We assume the null is true. If our P is low, we can reject that. And if we reject that, we believe the alternative is true. If we fail to reject, like is appropriate here, we can't say the alternative is true. That's really what we're saying. We don't want to accept the null. We don't want to say that we believe the mean is equal to $6,500. But we can't reject it and say that the mean is greater than it. So the wording we come up with is we say there's not enough evidence. And the wording I typically use, it's not magic wording. It just is pretty consistent and pretty easy to work with once you get comfortable with it. There is insufficient evidence to indicate that. And then you'll notice everything down here is exactly what the what the alternative hypothesis is saying, but I've just added the words of the problem. And a lot of times the easiest way to write this piece here is to go back up here and see what was asked and then copy and paste it. The average fee for a full service funeral in the current year exceeds $6,500. I can't say that here. Now, a couple questions for you. Hopefully that makes sense to you. Here's a couple questions. First, what assumptions are necessary for this analysis to work? What are the conditions? What are the things that we need to be true? And there's going to be several different assumptions that we look at throughout the course. There's 4 that we run into early on in the course, but right now there's really only 2 that you need to consider. This will change pretty quickly, but right now there's only 2. And the first one is random. We need random samples with everything we do. Well, I've been told here that I have a random sample, so I feel pretty good about that. Somebody randomly selected 36 funeral homes and collected the data, so that's fine. I'm not going to be concerned with that. Someone takes a random sample, good, we'll use it. The second assumption that we need to consider, we always need random, that's an easy one to work with, but the second one is about the population of X's. The funeral directors, when they give me their full service funeral fees, those are the data points, and that's the information I'm collecting. Those are referred to as the X's. The population of X's needs to be approximately normal. Now, that assumption is necessary, but it's only necessary if your sample size is small. Remember on the preceding slide, I said the way that the large and small work out, we're going to kind of do the same thing. The next example is a small sample problem. You're going to see the same kind of structure, the same steps, the same thought process. The only difference is here, because it's a large sample, I don't need to assume that the population of X's is normal. When I have a small sample, I will. And so this number here saves us from that extra assumption. If I sampled 20 funeral homes or 5 funeral homes, then I would need to assume that the full service funeral fees in the population were approximately normal. But because I sampled 36, I don't need that assumption. All right, so that's the first question. I said there was 2 questions I wanted to ask you. The second one is, what would change if I decided to change alpha, and let me make it a different color here. Oops, let's make it 0.10. There we go, that'll work. What if I decided to test at an alpha of 0.10 instead of 0.05? Well, that doesn't change this, right? My null and alternative would still be exactly the same. My test statistic, my p-value would still be exactly the same. Okay, same printout, same data. But what about now? When I look to see is p low, when I compared to the p-value to 0.05, it wasn't low. But what would happen if I compared the p-value to 0.10? Now all of a sudden it's low, right? 0.06 is lower than 0.10. So at 0.10, we would, and I would do this, at 0.10, let's see how I can do this and really screw up your notes. At 0.10, we would reject the null hypothesis. What would have to change with this wording over here? There is sufficient evidence to indicate that the average fee for a full service funeral in the current year exceeds $6,500. When P is low, reject. When P is high, fail to reject. The only wording that has to change when we're writing in the words of the problem here, the only thing that needs to change is that piece right there. If you reject, there's sufficient evidence to indicate that the alternative is true. When you fail to reject, there's insufficient evidence. So I like this wording so much. When I first write it, it's a little, I don't know, cumbersome. The word I tend to use is a little clunky. It's a little weird. It's like, gosh, there's a lot of words there. But it is pretty easy to work with once you get comfortable with it, and that's kind of the point. So hopefully this problem makes sense to you. Take a look at it. See how you feel about it. Let me take a look at one more. And so here, we're planning a new road through a European forest, as it turns out. And this particular forest has a lot of trees that are cut down, and so we want to minimize tractor skidding distances. If you have a real windy road and you have tractors that are skidding, that can be bad because tractors tend to skid in straight lines. And so the skidding distances in meters were measured at, look at that number right there, 20. Small sample. Again, am I using the right Sample size criteria, I am, because we're interested in the mean skidding distances. So we're measuring 20 randomly selected road sites. Recall a logger working on the road, and this is from a previous problem. Recall that a logger working on the road claims that the mean skidding distance is at least 425 meters. How would you write that? How do you write at least? Let's say at least. The logger claims that mu is at least greater than or equal to. That's what I would use, right? The logger claims the mean is greater than or equal to 425. That should probably be a period. Is there sufficient evidence to refute the claim? Apparently my punctuation is pretty terrible on this page of notes because that's a question mark. Is there sufficient evidence to refute the claim? If the logger claims mu is at least, this is the claim, is at least 425, and don't laugh at my writing, I'm using a mouse. And I'm using it very poorly, by the way. Anyway, the logger claims the mean is at least 425 meters. How do you say that's wrong? How do you contradict that? That's really what refute means. How do you say to the logger that he or she is wrong? Well, I think I would do a less than test. If someone says you're at least this, I'm going to say you're less than whatever that number happened to be. And so the test we're going to conduct here, and you'll see it here, is a less than test. And of course, that's what you see right here. Again, this printout didn't just magically appear to help us figure out the null and the alternative. It appeared because we went in and specifically said, let's do a one sample mean test. Let's compare it to 425 and let's do a less than test. So I asked for this printout. That's why it shows up there. And then once you have the printout, identifying the test statistic, identifying the p-value, very straightforward. Piece of cake. Piece of cake at that point. Okay, formulating a test. This is big. This is number one, right? You got to do that. That's a terrible asterisk. But that's the first step. That gets the printout. You get the test statistic. You get the p-value. Now you interpret it. Is p low? Looks like a pretty small number, but let's check. We're comparing it against a 0.10. Yeah, it's low. P is lower than 0.10. P is low. Reject the hoe. If the alpha here was 0.01, boy, it'd be close, but p would be high in that case, just barely. So you always have to compare the p-value to your alpha, but in this case, p is low, so we're going to reject. How do you say it? What's the wording? Before you look at the great time to pause this video. Pause it. What would your conclusion be? At alpha equal 0.10, we reject. There is, now fill in the blank. Test yourself. I'm not going to be there doing it for you on exams, on your projects. You're going to have to test yourself. Pause and then come back. Wonder how many of you actually paused there. I think I'll just go out on a limb and say thank you to both of you who did that. What do I get? I get this. We reject. There is sufficient. Remember, when we reject, there's sufficient. When we fail to reject, there's insufficient evidence to indicate that. And then everything after that, this part that's underlined here, the average skidding distance of all tractor trailers is less than 425. We reject H0. There's sufficient evidence to indicate that the average skidding distance of all tractor trailers is less than 425 meters. That's the conclusion that would be appropriate in this particular problem. Now, last question. What assumptions are necessary? Okay, let's kind of go through it again. There's only two that you really need to worry about now. Again, we'll expand this later. Do you think we're going to need a random component? Yeah, absolutely. However, again, in this particular problem, right here, we're told that these were randomly selected. You don't want someone going out there and saying, hey, let's find the 20 biggest skidding distances, or let's find the 20 smallest skidding distances. You want a nice random sample of skidding distances. Some of the small ones, some of the large ones, probably a lot of the middle ones. All right, so the random part appears to be satisfied with the way that the data was collected. What's the other assumption? Do we need normality here? Is there normal assumption? And I'm kind of torn here because when I refer to it as a normal assumption, I do that because it helps you guys remember the different assumptions that are necessary. There's a random assumption, there's a normal assumption. Later on we'll talk about an independent, we'll talk about an equal variance assumption. So there's kind of these buzzwords or phrases, keywords that help you to remember the different assumptions, but I want to be careful because when I say there's a normal assumption, the normal piece, and it actually is approximately normal piece, is just part of it. What needs to be approximately normal? And the answer to that is we make interpretations about means. You see the word here, average. If you go to the last problem, you see average full service funeral fee. So we make conclusions, we make interpretations in our confidence intervals about means. We make assumptions about x's. This is kind of an important point here. We make assumptions about x's. What are x's? X's is the data. If I'm interested in learning about the average GPA of all students, that's mu. If I need to make some assumptions, I'm going to make it on X, individual GPAs. Your GPA is an X. The average of all is a mu. We make conclusions on mu. We make assumptions on X. And so it's the skidding distances. Those are the X's. That skidding distance that we measure, one of the values here I just happen to remember, it's 488 meters. Okay, I think that's the problem we looked at with the confidence intervals. 488 meters, that's an X. The population of all X's. The shape of the distribution of all skidding distances needs to be approximately normal. If that's true, this works like a champ. Everything's great. If that's not true, if the skidding distance population isn't approximately normal, then we need to get back to work because we got to make this number bigger than 30, or at least 30, so that we don't have to worry about that assumption. That's how it all ties together. The way that we actually do it, the test statistic, the p-value that we make our conclusions, doesn't matter if it's large or small. We do it exactly the same way. Now, the computer used a different distribution, or should use a different distribution when calculating test statistics and p-values and confidence interval endpoints, but the way that we interpret those results is the same. All right, that's what I wanted to cover in this video. Now it's your turn. Now you can show me how much you want to get a good grade in this class, because what you do between now and the next time I get you a lecture, regardless of the format that it's in, the next time we're together, whether it's in live or probably online, you need to do a little bit of work. You need to do some examples. Take a look at some of the homework problems. Practice. Practice, practice, practice. For most of us, we need to practice this stuff. Very few of you guys just pick up this stuff and run with it. Some of you do. Some of the weirder ones among you, but most of you need to practice a little bit. So put some time in. Try some homework problems to see how you do. If you have questions, you know how to get hold of me. All right. Good luck. Bye.